Welcome to Topic 5.
If you thought this last unit was radical,
This one is
exponentially better!
When we converted between mixed and entire radicals, we used exponent laws. We said, yep, we can just do that. But aren't radicals and exponents different things? Thing is, there's actually a direct connection between them. And it's pretty wicked. Some might even say radical. Yeah, I know I've used that joke before. It's limited jokes. So let's assume that an exponent exists. That if we take the square root of something, that it's the same thing as taking that thing to some sort of power. We're going to assume that's possible. And we'll figure things out from there. Well, here's the thing. We could square both sides. So I could take this left side and square it. Left side. Right side. Take the left side and square it. Which means that if I do it at the left side, I have to do that to the right side as well. On the left side, we're saying we're taking the square root to the power of 2. Those cancel each other out. We're just left with x itself. On the right side, by the power laws, since we've got power of a power, we're going to multiply those exponents so that I have x to the power of 2 times a, or just 2a. Now, worth noting is that the exponent here, on the left, is a 1. And in this statement right here, we're saying that x to the power of 1 is the same thing as x to the power of 2a. Well, that must mean that we're saying that 1 is the same thing as 2a. And if we divide both sides by 2, we can then say that a is equal to 1/2. So our big conclusion here is that taking something to the power of 1/2 is the same thing as taking the square root of it.
Whoa.
Yeah.
Wouldn't that be cool if we can do a similar thing, but instead of for square roots, we could do them for cube roots?
Dare to dream.
Dare to try it.
Okay.
So let's give it a go. Let's say if I had x to the power of something, let's say that something's a, what would that a be to make that equivalent to the cube root of x? So we're trying to find a value for a in which when we take x and raise it to the power of a, it is equivalent to saying we're cube rooting that value of x. Now, we're going to do a similar thing like Mr. A did above and said, well, what if we took what we started off with and let's try and get rid of this radical side. So instead of squaring the square root like Mr. A did, that wouldn't actually get rid of this cube root. So to get rid of a cube root, we would have to cube it. So let us cube. And if we do that to the one side, we've got to do it to the other, because otherwise it's just not fair. Now, on my right-hand side here, if I have a cube root and I cube it, those two processes undo themselves. So we end up with just x, secretly to the power of 1. And on my left-hand side, by exponent laws, I'm taking x to the power of a and raising it to the power of 3. So I multiply those two exponents to give me x to the power of 3a. And in the same sense, if I'm saying x to the power of 3a is equal to x to the power of 1, that must mean my 3a is equal to 1. My exponents of both of those are equivalent. Now here I can just solve for a. Right now, a is being multiplied by 3, and do it by dividing by 3. A is equal to 1/3. Whoa. So my exponent that would allow me to state that x to that exponent is equivalent to the cube root of x would be 1/3. So I could say x to the power of 1/3 is equal to the cube root of x. Dope.
Now, if you want, you can take a moment and see if you can develop a general rule down here. See what you can do. But we're going to do that for you as well. The kickoff of this would be to say that we can find an exponent that would in general work for the nth root of x. So whether we're working with the 4th root, or the 5th root, or the 6th root, or any kind of index there, we can always get a related exponent. So from that, see if you can actually develop the rule. For the nth root of x, what is the equivalent exponent? Of course, I will now dive into this, but in a different color.
You could have just changed the style.
I know. I'm just not used to it yet. I'm like my parents when they find something new for their phones. And they keep doing it the old way, but it's okay. I don't mind becoming my parents. They're pretty cool. All right. X to the a is the same thing as taking the nth root of x. To get rid of a square root, we squared both sides. To get rid of a cube root, we cubed both sides. To get rid of a 4th root, we would take both sides to the power of 4. To get rid of an nth root, we would take both sides to the power of n. I could do that on the next line. So we're going to take this left side to the power of n, and that's because we're taking this right side to the power of n. As a result, on the left side, by the power of a power law, we have x to the power of an, and on the right side, well, we just have x, which is, of course, to the power of 1. Since x to the an is equal to x to the 1, we can say that an is equal to 1, and our whole mission here was to find what a could be. So we'll divide both sides by n, and say a is 1 over n. And what we've essentially said here is that if you are taking the nth root of x, that's the same as taking x to the power of 1 over n.
Interesting. So what you're saying is every single time we have some sort of radical, to write that instead as some kind of some sort of exponent or power, we just take the index and put it in the denominator.
That's legit. That is what I'm saying.
Whoa. So I wonder, do you think that numerator always has to be 1?
I honestly have no idea, but I'm hoping you can tell me.
Oh, trust me. I can tell you. Well, let's just say, here we had the nth root of x, and that's equivalent to x to the power of 1 over n. Well, what if in some case, maybe this one perhaps, instead of saying the nth root of x, let's just say x is equal to maybe some other variable y to some other exponent m. So instead of looking for the nth root of x, we're actually going to look for the nth root of y to the power of m. See if we could introduce some other exponent in here and see what happens. Now, if I were to do that, knowing what we've kind of derived on the previous page, instead of writing it as the nth root of x, I can rewrite this as x to the power of 1 over n. And in the same way, on my right-hand side, I could take my radicand, y to the power of n, and say, well, that's just the same as the nth root of y to the power of m is the same as y to the m to the power of 1 over n, because my index becomes my denominator of this kind of fraction. Right? Same, nothing really changed. But let's take a look at what's going on that right-hand side. Well, on that right-hand side, we have a power of a power. We're raising that exponent, m, to the power of 1/n. And when we do that, what we do is we multiply these exponents. So we end up with y to the power of m over n. Right? So what happens here is, check this out. This m doesn't necessarily always have to be the number 1. It is physically possible, maybe not physically possible, well, I guess it's physically possible, but mathematically possible to have some sort of numerator that isn't equal to 1. And remember that m is just kind of a placeholder. We could put any number in there. We could put 3, 7, 252, 971. We could put anything.
We're going to tackle some examples, and we'll just put this into action. Like so. So given this radical form, how could we write that with exponents instead? Well, we're going to use this general rule that was just developed that says the index becomes the denominator of this fraction, and this exponent here just stays as the top part of the fraction.
One thing that we should keep in mind is those 4 things that we just did were to help develop this rule. Right? It's not that we're going to necessarily ask you to redevelop the rule, but I think something that we find valuable is not just telling you that math exists, but showing you where it comes from. So maybe you completely understood everything we've done thus far, and maybe you're still a little bit confused. It's not going to be the end of the world if you're still not 100% certain on that derivation and where that math exactly came from, but hopefully you understand that we didn't just pull it out of thin air. There is some sort of mathematical procedure that we can do to obtain the rule that we have on the sheet right in front of you right now.
That's legit. All good knowledge is based in a rock-solid understanding. So if you have that, it makes that knowledge easier to recover. Let's look at this. So the rule says that the nth root of x to the m is equal to x to the m over n. We don't really need to write this, but I'm writing it there just so we can see the similarities. Because if we parallel that with this example we have, it's like this 3 is our n, it's like this 7 is our x, and it's like this 4 is our m. So when we express that in exponential form, our radicand gives us the base. So we've got 7. M is 4. And n is 3. So again, noting that the index becomes the denominator, and this exponent goes to numerator.
Something to watch out for, especially when you're writing fraction exponents, is that you are making sure that those 4/3 are super tiny as an exponent. You're not going to write 4/3 something like this, because then this tends to look more like a mixed fraction, right? Even though this is a little bit bigger than the bottom line here, they're kind of hard to distinguish. So when you are writing your exponents, please make sure that your fractions are super itty bitty, but also written as exponents.
Feel free to give the next 3 a try, and then we'll put solutions up momentarily. Well, here I go. I'm going to write this as an exponent. So 8's my base, 2 is in the numerator of the fraction, and the denominator of the fraction is the index of the radical, which was 5. Whoa, hey, yo, I don't see an index here. That's scary. Just kidding. We know that that index is really 2. So no index indicated, that's a square root. Our base is 5, numerator is 9, and denominator of that fractional exponent is 2. And then last one, the base is 2, because that's our radicand's base, and we've got 3 over 8 for our fractional exponent.
So what we've done so far is we've gone from radical to exponent. In the same idea, we can also go backwards. So let's take a look at that rule again, that kind of generalization saying the nth root of x to the power of m is equal to x to the power of m over n. Well, now we're just going backwards. We're saying whoop, whoop. Let's start with my exponent or my fractional exponent and then get to a radical. And again, we can parallel that with this example. In this example, my 9 would be equivalent to my x here. My m would be equivalent to this 6. And my n would be equivalent to this 11. So trying to figure that out, that 9 will take that place of my x, which is the base of my radicand. My exponent's numerator, that m will become my exponent of my radicand. And my denominator will become the index of my radicand. Oops, I put m instead of 6. And so that denominator 11 will be the index of my radicand. Okay, so hopefully you can see the similarities between them. Take a moment to try the next 3. Did you do it? Yeah, you did. All right, and we're going to put up some solutions here. Oops. So I have my radical. I always like starting with my denominator to figure out the index. My index is 2. Keep in mind that when I have an index of 2, it is proper form to not include that index. So I'm not going to write it there, but I know that 2 exists. Then my radicand is going to be 3 to the power of my numerator, which is 3. This next one here, f, well, I have my radical. I like to start with my index, which is the denominator. That's going to be 7. My radicand's base will be 2. And my radicand's exponent will be that numerator, which is 4. And last but not least, starting with my radical, again, my denominator is my index. So I have 9 as my index. My base is 13. And my exponent would be 5, which is the numerator.
So we're going to do some examples of actually evaluating some powers based on these fractional or rational exponents. And we're going to be able to do this without having to use a calculator or other device as a resource, because we'll know how to take square roots or cube roots, even fourth roots. So if we wanted to evaluate something like 25 over 121 to the power of 1/2, what a doozy! Well, by the power law, or by the power of a quotient law, we can say that this 1/2 applies to the top and to the bottom of a fraction, which is why we've got it on both of those. And by our newfound rule that says taking something to the power of 1/2 is the same thing as taking a square root, we can say that 25 to the 1/2 is the square root of 25. We can say that 121 to the 1/2 is the square root of 121.
Oh, that's much less scary.
Yeah, it's not even the worst thing ever.
Look, they're even perfect squares.
It's beautiful, because then we can say that the square root of 25 is just straight up 5. And we can say that the square root of 121 is just straight up 11. So we just evaluate each radical, and then this one is done.
Wow, that's not bad at all.
Hey, you want to try it?
Honestly, yeah. Let's start with this guy.
Okay.
So, take a couple seconds actually right now to try some of these on your own.
Smart.
Honestly, I think you're more than capable. I have full confidence in you. That was it. That was your cue to that was your cue to start.
I think they started. Do you think they started?
I think they finished. This is your cue to come back. So here we go. My first step is to rewrite this as a radical, because I don't really know how to evaluate it as a fractional exponent, but I'm set with radicals. So if I'm rewriting this as a radical, I know that my denominator becomes my index, so this would be a square root, but we don't write the index of 2. We can, because it's not our final answer, but typically we don't. And my base of my radicand is going to be the 16 there, and my 16 is going to be taken to the power of 1. 16 to the power of 1 is just 16, so I also don't have to write that exponent. Well, the square root of 16, trust me, that's 4. And that's it for that question. Oh, baby. Oh, look at this one. What a beauty. Now, I have negative 125 taken to the power of 1/3. I panic a little bit, but then I realize I got this. I know that my denominator of my fraction is going to become my index. My radicand is going to be, or the base of my radicand is just going to be the base of my exponents, so the negative 125, and I have that to the power of 1. It's important that, in this case, it's taken to the power of 1, so it doesn't actually change the value. But if this was taken to the power of 2 or something like that, it's important to have these brackets here. Okay, so I'm going to include them, even though that power of 1 doesn't actually factor in to change my answers at all. But just in case this was like a 2 or a 3 or a 17. Now, what's the cube root of negative 125? Well, I know the cube root of positive 125. Well, that's just 5. So negative 5 times negative 5 times negative 5 would be my cube, or negative 5 would be the cube root of negative 125.
Nice. Maybe I'll jump in here with some roots of integers. Oh, psych, it's a fraction. I've been had. But we can still do this same way. So, as in the example above, that's printed out there, we'll use the power of a quotient law to say that we've got 81 to the power of 1/4, and that's being divided by 625 to the power of 1/4. Which means that we are taking the 4th root of 81 over the 4th root of 625. 4th root, my goodness, how on earth do we do this? Well, you could do a guess and check of what number times itself times itself times itself gets you the value you're after, like 81 or 625. You could also say that if you want to take the 4th root of something, you take the square root and then take the square root of that. So square root of 81 is 9. The square root of 9 is 3. So we could say that the 4th root of 81 is 3.
Oh, I've never actually thought of it that way.
Yeah, it's a pretty sick trick. It's based on the exponent laws, and yet it's pretty radical. I will never stop telling that same radical joke. Same. 4th root of 625 is equal to the square root of 625. Square root of 625 is 25. And square root of that, these days, is 5. This one is dun 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 dun. Zoom. Oh my goodness. This one looks scary. I don't even, decimals? You know what? No, I don't want it as a decimal. I'm going to write this as a fraction because I think that might help me figure out what's going on here. So 0.027 is 27 over bloop, 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 1,000. I lost my line. So 27 over 1,000 to the power of 1/3. Yeah, I can see this now because I can see that 27 is a cube that I'll be able to evaluate, and so is 1,000. So what I'm doing here is I'm just going to jump straight to this part, the cube root of 27, and dividing it by the cube root of 1,000. And I know that the cube root of 27 is 3. I know that the cube root of 1,000 is 10, because 10 times 10 times 10 is 1,000. And we could leave it in this form. This form is okay. But generally speaking, it's good to put it back in the form it was given to us. So it was given to us as a decimal. We should represent it as a decimal if we can. If it was given to us as a fraction, represent it as a fraction. In this case, we can represent this as an exact decimal, and that is 0.3. Oh, here's my box.
Wow, all of these exponents had a numerator of 1. I can't wait to try another one with a numerator of 1.
It's different.
But that's okay. So what I'm going to do is kind of the same thing. I don't know how to evaluate 4 to the power of 3/2, but I know how to evaluate it if it was in its radical form. So just like that generalization of the rule on the previous page, we can rewrite that as a radical. So I like to start with my index. My index in this case is 2. I don't write that down. And I write 4 to the power of 3. Now, what I can do is a couple of things. I can either take care of that radical first, or I could take care of that exponent first. And typically, I do whatever is easiest for me when I look at it. I'm going to do both to give you some options, because you got options. And if I'm taking care of, let's say I'll do the radical first here, and then I'll do the exponent first in this case. So if we're taking care of the radical first, what's the square root of 4? Well, the square root of 4 is just 2. And I still have my exponent, so 2 cubed. And 2 cubed, well, that's just 8. So I can say that 4 to the power of 3/2 is just 8. But what happens if I took a look at that exponent first and said, well, instead of doing the square root of 4 cubed, what if I did 4 cubed first? And so 4 cubed, 4 times 4 is 16, times 4 is 64. So now I get the square root of 64. And the square root of 64 is 8. So it actually doesn't matter which route we take first if we do the radical first or the exponent, hey, get away from here, first. Whatever is easiest for you and whatever you see as a good opportunity to proceed.
Do you have a preference?
I personally like to do the radical first if possible because, take a look at this, I dealt with smaller numbers.
Yeah.
Right? Say this was maybe like, I don't know, a 16 instead of a 4. I don't want to do 16 cubed. But if I could take the square root of it first and be like, okay, that's just going to be 4 cubed, then it kind of helps me proceed. So it doesn't really matter, but in terms of dealing with smaller numbers, this radical route is the most radical of them all.
Wow. Get new material. I would never tell the same joke twice.
Oh, I would. All right. Whoa! Whoa, whoa, whoa. I thought we were doing exponents that were fractions, not these decimals. Luckily, we could actually convert that to a fraction. We know 1.25, that's like 1 1/4.
Yeah, I've got $1.25 in my pocket.
And 1 1/4 is just 5 quarters. So I can rewrite that as 81 to the power of 5/4, right? Because 1.25 is, you could even think about it as 125 over 100. And, reduce that as much as possible. They're both divisible by 25. There's 5 25s, 125, and 4 25s in 100. So you could think of it that way. Or you could think of it in terms of money, and you could know, well, that's just 5 quarters. All right. Either way, we can represent that instead of as an exponent as a radical. My index here would be 4. My radicand's base would be 81, and my radicand's exponent would be 5. Like I said before, you do have the choice of going with the radical first or the exponent first, but I will tell you personally, without a calculator, there is no way I'm taking 81 to the power of 5 and then trying to figure out what that fourth root is. That just seems bananas. So what I'm going to do is I'm going to deal with that radical first to make the number smaller. Well, I know the fourth root of 81, well, it's just 3. So I could rewrite that as 3, but I still have that exponent of 5 I haven't dealt with. And if I'm taking 3 to the power of 5, 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 is 243. And here we have it, folks. Math. And here we have it again, practice.
Ooh.
Whoa. So in the textbook, there are some questions that you would be able to do with all of your newly acquired skills. This reflect here doesn't just mean for you to sit and reflect on your learning, although that is suggested. But there is a portion of the textbook that does have a section that's called reflect, and that just indicates that you should maybe do it.
Yeah. You'll find it somewhere after question 18. I'm not sure exactly where, but it's in there.
Otherwise, we hope you have an extremely radical day. And that may be my last radical joke. I'm lying.
I hope that all your days get exponentially better.
We're not lying. Okay, bye!
Toodles.